Hello everybody, welcome to exam 1, question 3. Today we are going to be talking about action potential. So let's start off by drawing what an action potential looks like on a graph. So here's a graph, and we're going to say this is our action potential. So just like this. Alright, so let's start off with talking about this action potential. So we start off here. So point 1, this is our resting membrane potential. So theoretically in a lot of cells this is about -70 voltage, and this is where we start off. And as you can see, we start to immediately have a climb. So whenever you start going towards 0 and start heading up from our resting membrane potential, this is what we call depolarization. This is depolarization as we're going from -70 all the way up to 0. And at this point in time, what's happening is that we are opening up Na channels. So Na channels are very positive. So as they are fleeing from the cell, we immediately start to jump up into more positive. Now, this dotted line is very important. This dotted line is the threshold. And once we're able to hit threshold, which is what happens here at number 3, as number 2 is Na channels opening, number 3 is when we reach threshold. That's when we start climbing a little bit and starting to depolarize a little bit, and that gives us our action potential. And so, as you can see, all through this big old line going up, this is our action potential. This is us releasing Na+. Now when we get about, let's say about here where number 4 is, we're starting to get very high and very polarized. And at this point in time, Na channels are gonna start to shut down a little more. We've gotten very high and we've hit that action potential. So Na channels are gonna start closing here. And so what happens is that we start to depolarize. And it's very important because now up here in step 5, this is when we start to add K. So what happens is K is super negative and it's gonna bring us all the way down. But as you can see, K brings us not only below threshold, but it brings us below RPM, and it brings us all the way down here to 0.6. Now this is hyperpolarization. So what happens is we have all the K channels open, and somewhere around here, let's call this one 6 and make this one 7. So somewhere around 6, the K's start to close, but they don't fully close, and so it keeps going down, and then we have hyperpolarization at number 7. And then down here, number 7, that's when the K fully closes as well, and we start to go back up. So we're back here, we'll call this 8. 8 is back to our resting membrane potential. So it should be equal to back where we start at number 1, and this is the full action potential. Now something very important about action potentials is knowing terms. As I said before, this is depolarization when you go up. You're going from the resting membrane potential and you're going up, you're depolarizing it. When you come over here, this is called repolarization. So we call this repo. So repo is going back towards the resting membrane potential and back towards our line here. And way down here where number 7 is, this is called hyperpolarization. As you can see, hyperpolarization is when we go under our resting membrane potential. As you can see, we're a little lower than it, and that is depolarization, repolarization, and hyperpolarization. Now something very important about action potentials is that it'd be very bad if we constantly had action potentials. Our bodies would probably just freak out and our systems would be all over the place. So our body has built-in times where we can't have action potentials, and these are called refractory periods. Now there's 2 refractory periods as I redraw our action potential. So let's draw it one more time. So now we have the first one, which is absolute refractory. So we'll call it ARP. So absolute refractory period, this is the first time in which we can't have another action potential happen, and it occurs here. So whenever you are depolarizing, so depot, or whenever you're repolarizing, repo, this is when ARP happens, and this is preventing us from having two action points back to back. Now there's also a second type of refractory period, and this is called relative refractory period. So this is RRP. It happens here in our hyperpolarization. And as I said before, these are very important because we can't have back-to-back action potentials, or that'd be very dangerous. Now there's some terms that we're going to talk about that relate to these action potentials. So let's get to those as well. Our first one is going to be called conductance. So I'll go ahead and we'll go ahead and label these three very important things for action period. So let's start with conductance. So here's conductance. And so what happens is conductance is about ions moving across the channel. So we'll put that. So now this is a report. I'll draw an example of this. So let's say this is our ion channel, and this is our NaCl channel. So if we're at resting membrane potential, so say we're at -70, then what's going to happen is that Na is going to be more powerful than K, because in channels anything can go backwards and forwards and they can go through it. But it's very important. Conductance focuses on the voltage of this cell and this channel. So at -70, NAs would be more powerful and would go in and out freely and would push Ks out of the way. So Ks would not be able to go through. However, if we made this into something above 0, a positive, let's just make it +70, then what would happen would be the reverse, where Ks would be able to go in and out. Good thing my Ks look like my Ns. And then NAs would not be able to go in and out, as Ks are more powerful. So the important thing about conductance is that when we have more movement, we have more conductance. So I'll also write that here on the board. For movement, conductance goes up. Okay, let's talk about our second term. Our second term is going to be capacitance. So we'll put that one here. Now, what is so important about capacitance? Capacitance is the ratio of separated charges between positive and negative. And this one has a formula, so let's write that formula out. So capacitance, which is C equals Q divided by V. So as I said before, C is capacitance. Q stands for the amount of charge separation. And V stands for the voltage between surfaces. That is very important. As I said before, capacitance is about the separation of charges, and through this formula we're able to see how much charge is between the voltages and how much is between the surfaces. Now we have two more formulas that we're going to talk about. Let's talk about time constant. Now time constant also has a formula. So this formula is Rm times Cm. And now what's very interesting is Rm actually is resistance membrane. And Cm is actually capacitance of the membrane. And in this formula for times constants, the Rm and the Cm always equal each other. And this is very important. It helps us know the resistance of the membrane and also the capacitance as well. And we have one more formula, so I'm gonna erase everything on our board for us. And our last formula that we're gonna talk about is our length formula. So the formula actually has some very similarities to capacitance and to our time constant as well. So length, it also has a formula. Oh, we can never spell length. Length is our RM divided by RI, and then 1/2 of that. And so in this formula, Rm once again is the resistance of the membrane. And we have a new one, Ri. Ri stands for the internal resistance. And length constant, what this is used for, is the time in which it will take for something to depolarize. So it's very important. It can help us know how long an action period is, how long it's going to take for an action period to depolarize, and so on. And this is for question 3, and thanks for watching.